Section 5.5, Hyperbolas. Part 1, Introduction to Hyperbolas. The hyperbola as a conic section. If we take our double-napped cone and we slice it by a vertical plane, straight up and down, not going through the vertex, we get a hyperbola. Notice the hyperbola has two different branches. The geometric definition of a hyperbola says that given two distinct points, F1 and F2, so those are the two focus points in the plane, and a positive number d that is smaller than the distance between F1 and F2, a hyperbola is a set of all points x, y in the plane such that the absolute value of the difference of the distance from F1 to xy and the distance from F2 to xy is d. So if I have this point x1, y1 on the hyperbola, the difference between these two distances, so the distance from F1 to that point and from F2 to that point, if we take the difference of those two distances, that is always a constant, no matter where that point xy is on the hyperbola. The difference between those two distances is always the same. For just some definitions, the line that passes through the foci we call the transverse axis. So on the picture on the left, that is that horizontal line that's dashed, that's our transverse axis. And the point that is equidistant from the two foci is the center of the hyperbola. That's this point right here. The 2 points where the transverse axis intersect the hyperbola are the vertices. So here's our 2 vertices. And notice the hyperbola opens around the 2 focus points. And then the conjugate axis is perpendicular to the transverse axis and goes through the center. Now on the picture on the right, you can see this box, and you can see that we have 2 asymptotes that are the diagonals of that box. So a hyperbola has 2 asymptotes, and we'll talk about how to draw that box and how to find those 2 asymptotes so that we can draw the hyperbola. The standard equation of a hyperbola with a center at 0, 0 looks like this. For a horizontal hyperbola, so one that opens right and left, we have x squared over a squared minus y squared over b squared equals 1. And for a vertical hyperbola that opens up and down, we have y squared over b squared minus x squared over a squared equals 1. So the horizontal hyperbola, where the x squared term is positive, opens right and left. The vertical hyperbola, where the y squared term is positive, opens up and down. Now, if we look at the box, let's look at this picture on the left and look at that box that was drawn. So the distance from the center to the vertices was a. That's the direction, the number that's underneath the x squared. And then the vertical distance here is the number that's underneath the y squared. And then c is the distance from the center to the focus, same as with an ellipse, but now c is equal to the square root of a squared plus b squared. So let's write an equation for this hyperbola in standard form, and then we'll find the value of c. So the hyperbola is opening right and left, so we know the x squared term will be positive. So let's find out what goes underneath the x squared, that's the a squared, and what goes underneath the y squared or the b squared. So the horizontal distance from the center is 2. So underneath the x squared, we have 2 squared. And now I'm going to draw the box. So I'm going to go from that vertex, I'm going to go up till I reach the asymptote. That distance right here is what goes underneath the y. Remember, the asymptotes are the diagonals of that box. So this is what that box would look like. The horizontal distance is 2. The vertical distance of that box, 1, 2, 3. So 3 squared goes underneath the y squared. So I could write my equation as x squared over 4 minus y squared over 9 equals 1. Then it says to find the value of c. So c would be the square root of the sum of those two numbers, 9 plus 4, which is the square root of 13. So that means the focus points are square root of 13 away from the center. Let's try another one with a vertical hyperbola. So the vertical hyperbola will have a y squared over something squared minus the x squared over something squared equals 1. Now the distance from the center to that vertex, 1, 2, 3, is 3. So underneath the y squared, I'll put 3 squared. And then I'm going to go from there until I reach the asymptote. That is how I'm going to draw the box. So that box is not part of the hyperbola, but it will help us to figure out these distances, the horizontal and vertical distance. And when we don't have the asymptotes, it will help us to draw the asymptotes if we draw the box first. So that red box is not actually part of the hyperbola. We're just using it as a guide with the graph. So underneath the x squared, I need that horizontal distance from the center to that box. So 1, 2, 3, 4, which is, so 4 squared goes underneath the x squared. I have y squared over 9 minus x squared over 16 equals 1. And then the c value would be the square root of 9 plus 16, or the square root of 25, which is 5. So the focus points are 5 units away from the center. 1, 2, 3, 4, 5. Here's one focus point, and here is the other focus point, and the parabola opens around those two foci.